Hello, and welcome. It's good to have you here, wherever you are right now. Perhaps you've had a long day, or perhaps your mind is simply full of thoughts that won't quite settle. Either way, you're welcome to stay as long as you like, or to drift away whenever you feel ready. There's no pressure here, no urgency. We're going to spend some time together exploring something vast and quiet and beautiful, something that exists far beyond the edges of our daily concerns. We're going to talk about interstellar dust clouds, those enormous, gentle structures that float between the stars. And I promise you, there's nothing here to worry about, nothing to solve, only soft facts and quiet wonders to let wash over you like a calm tide. If you'd like to follow along for more of these gentle journeys through science, you're welcome to, but only if it feels right. No obligation, no expectation. Just know that there are more stories waiting whenever you need them. Now, let us begin slowly and softly with the dust itself. Interstellar dust clouds are made of the smallest things you can imagine. Particles so tiny that millions of them could rest on the head of a pin without crowding. These grains are mostly less than a micrometer across, smaller than a single cell in your body, smaller than a grain of pollen floating through a summer afternoon. And yet, gathered together across distances so vast they dwarf our comprehension, these tiny specks form clouds that can stretch for dozens or even hundreds of light years. It's a strange and soothing thought, isn't it? That something so small can, in great numbers and with enough time, create something so immense. These clouds drift through the space between stars, not empty space as we once imagined, but a place filled with whispers of matter, thin beyond belief, but never truly absent. In every cubic centimeter of these clouds, there might be only a few dozen atoms, sometimes a few hundred, sometimes a few thousand. Compare that to the air around you now, where every cubic centimeter holds billions upon billions of molecules, and you begin to understand just how delicate, how sparse these cosmic clouds really are. They are more emptiness than substance, and yet they glow, they shape light, they give birth to stars. They are patient in a way that nothing on Earth can be. The dust grains themselves are ancient travelers. Many of them were born in the outer atmospheres of old, dying stars, stars that swelled up as they aged and gently puffed their outer layers into space. As those layers cooled, atoms began to stick together, carbon to carbon, oxygen to silicon, building tiny solid seeds in the darkness. Other grains formed in the violent winds of supernova explosions, where atoms were flung outward at incredible speeds and then, in the cooling aftermath, condensed into microscopic particles. So when you think of interstellar dust, think of it as stardust in the most literal sense, the ashes and exhalations of stars that lived and died long before our sun ever formed. These grains are not uniform. Some are made of silicates, rocky materials similar to the sand on a beach, though far, far smaller. Others are carbonaceous, rich in carbon, resembling soot or graphite. There are grains coated in ices, water ice, carbon dioxide ice, methane ice, frozen onto their surfaces in the cold of space. And there are grains that contain complex organic molecules, the building blocks of chemistry that, in the right conditions, can lead to life. The diversity is quiet but profound, each grain a tiny world of its own, with its own history, its own composition, its own journey through the galaxy. Light behaves strangely around these clouds. When starlight passes through a region filled with dust, the blue wavelengths scatter more than the red ones, the same reason our sky is blue during the day. But in space, this scattering means that stars seen through a dust cloud often appear redder than they truly are, their lights softened and shifted, as if the cloud has placed a gentle filter between us and them. Astronomers call this reddening, and it's one of the ways we know a dust cloud is present, even when we can't see the cloud itself. The cloud announces itself by changing the light, by whispering to us through the colors of distant stars. Some clouds are so thick with dust that they block light almost entirely. These are called dark nebulae, and they appear to us as black patches against the starry sky, voids where no stars shine. But they are not truly empty. They are full of dust and gas, cold and dense, waiting. The most famous of these is probably the Horsehead Nebula, a dark silhouette shaped, by chance, like the head and neck of a horse, standing out against a backdrop of glowing gas. It's a reminder that even darkness in space is not nothing. It's matter, its presence, its potential. Other clouds glow softly with reflected light. When a dust cloud happens to be near a bright star, the starlight bounces off the tiny grains and scatters in all directions, creating what astronomers call a reflection nebula. These nebulae often appear blue, because blue light scatters more efficiently off the small dust grains. The Pleiades star cluster, that little dipper-shaped group of stars you can see on a clear winter night, is surrounded by such a cloud. The stars seem to be wrapped in a faint blue haze, a delicate veil of light and dust, gentle and beautiful. The temperature of these clouds is another soothing fact. In the densest, darkest parts of a dust cloud, far from any star, the temperature can drop to just 10 or 20 degrees above absolute zero. That's around minus 260 degrees Celsius, colder than anything we can easily imagine, colder than the coldest winter night, colder than the surface of Pluto. At these temperatures, atoms move so slowly they barely vibrate. Molecules freeze onto the surfaces of dust grains. Everything is still, quiet, waiting. It's a kind of cosmic hibernation, a deep rest that can last for millions of years. And yet, even in this cold stillness, chemistry happens. On the surfaces of dust grains, atoms meet and bond in ways they couldn't in the gas alone. Hydrogen atoms land on a grain, slide slowly across its surface, and eventually find each other, forming molecular hydrogen, the most common molecule in the universe. Water forms this way too, oxygen meeting hydrogen on a frozen grain, building ice molecule by molecule. The dust grains act as tiny laboratories, catalysts that bring atoms together and hold them long enough to react. It's slow, patient work, but over millions of years, it adds up. The clouds grow richer in molecules, more complex, more interesting. These clouds are not static. They move, they flow, they swirl in response to gravity and magnetic fields and the pressure of starlight. A dust cloud can be stirred by the winds from a nearby star, or compressed by the shock wave of a distant supernova, or pulled into a spiral by the gravity of the galaxy itself. They are dynamic, but in a slow, graceful way, changing over thousands or millions of years, far too slowly for any human eye to see, but changing nonetheless. If you could watch one of these clouds over deep time, you would see it breathe, expand and contract, twist and reshape itself like a living thing, though it is not alive, only responsive to the forces around it. Magnetic fields thread through these clouds like invisible scaffolding. The dust grains, many of them, carry a slight electric charge or contain magnetic minerals, and they align themselves along the magnetic field lines, the way iron filings align near a magnet. This alignment affects how light passes through the cloud, polarizing it slightly, and astronomers can measure this polarization to map the magnetic fields inside the cloud, fields we could never see directly. It's a beautiful example of how we learn about the invisible by watching how it shapes the visible, by listening to the quiet signals the universe sends us. The clouds are also full of gas, far more gas than dust by mass. For every bit of dust, there are roughly 100 times as much gas, mostly hydrogen, some helium, traces of heavier elements. The dust makes up only about 1% of the cloud's mass, and yet it's the dust that dominates what we see, because dust interacts with light so effectively. The gas is mostly invisible, unless it's hot enough to glow or cold enough to emit faint radio waves. So in a sense, the dust is the messenger, the part of the cloud that speaks to us, that tells us the cloud is there at all. Some of these clouds are enormous beyond comprehension. The Orion Molecular Cloud Complex, one of the nearest large star-forming regions to Earth, stretches across hundreds of light years and contains enough material to make thousands of stars. If you could see in its entirety, not just the glowing parts but the dark dust as well, it would cover a huge portion of the sky, far larger than the constellation of Orion itself. But most of it is dark and cold, visible only in infrared light or radio waves, hidden from our eyes but not from our instruments. Within these giant clouds, there are smaller, denser clumps, regions where the dust and gas have begun to gather more thickly. These clumps are the seeds of stars. Gravity pulls them together, slowly at first, then faster as they grow denser. As a clump contracts, it heats up, and eventually, if it's massive enough, the center becomes hot enough for nuclear fusion to begin, and a star is born. The dust cloud, then, is a nursery, a place where stars come into being slowly and quietly over the course of millions of years. It's one of the most peaceful processes in the universe, and also one of the most creative. Before a star ignites, while it's still just a collapsing clump of gas and dust, the material around it often forms a disk, a spinning pancake of matter that feeds the growing protostar at the center. This is called a protoplanetary disk, and it's in these disks that planets eventually form. The dust grains in the disk stick together when they collide, building up into larger and larger clumps, pebbles, boulders, planetesimals, and finally planets. So the dust in these clouds is not just the raw material for stars, but for planets too, for worlds, perhaps even for life. Every planet in our solar system, including the Earth beneath your feet, began as dust in a cloud like this 4.5 billion years ago. The dust grains also play a crucial role in cooling the cloud. When the gas in a cloud gets compressed or disturbed, it heats up, and hot gas has more pressure, which resists further collapse. But the dust grains absorb some of that heat and radiate it away as infrared light, cooling the cloud and allowing gravity to continue pulling it together. Without dust, star formation would be much less efficient, much slower, perhaps even impossible in some regions. The dust, then, is not just a passive ingredient. It's an active participant in the process, a helper, a facilitator of creation. There are clouds that have been observed for centuries, their shapes and positions carefully recorded by generations of astronomers. The Trifid Nebula, the Lagoon Nebula, the Eagle Nebula with its famous pillars of creation, all of these are dust clouds mixed with glowing gas, regions where stars are being born right now, in our cosmic neighborhood. We can watch them, study them, learn from them. They are close enough that we can see details, structure, the intricate dance of light and shadow, the delicate balance of forces that shapes them. But there are also clouds so distant that their light has traveled for billions of years to reach us. When we look at those clouds, we're seeing them not as they are now, but as they were in the distant past, when the universe was younger, when galaxies were still forming, when the first generations of stars were just beginning to enrich the cosmos with heavy elements. Those ancient clouds are different from the ones nearby, less rich in dust, less complex in chemistry, because the universe hadn't yet had time to build up the heavier elements. The dust clouds, then, are also a kind of clock, a record of cosmic history. Each one is a snapshot of the universe at a particular moment in time. The dust clouds are shaped by the life cycles of stars in a beautiful feedback loop. Stars form from dust clouds. They live for millions or billions of years, and then they die, returning much of their material to space, enriched with new elements forged in their cores. This returned material mixes with the existing clouds, making them richer, more complex, and from these enriched clouds, new stars form, and the cycle continues. It's a kind of cosmic recycling, a process that has been going on for most of the universe's history, slowly building up the chemical complexity that makes planets and life possible. Some clouds are disturbed by the very stars they create. Young, massive stars emit intense ultraviolet light and powerful winds that push against the surrounding dust and gas, carving out cavities, sculpting the cloud into fantastic shapes. The pillars of creation in the Eagle Nebula are a perfect example. Those towering columns of dust and gas are being eroded by the light from nearby young stars, their surfaces slowly boiling away, even as new stars continue to form deep within them. It's a dynamic, ongoing process, creation and destruction happening side by side, neither one winning, both part of the same story. The dust grains can also be destroyed. When a supernova explodes, the shock wave that races outward can shatter dust grains, breaking them into smaller pieces or even vaporizing them entirely. But supernovae also create new dust, as we mentioned earlier. So even in destruction, there's creation. The balance shifts and flows, but the dust persists in one form or another, constantly recycled, constantly renewed. There's something deeply calming about the timescales involved. A dust cloud might exist for tens of millions of years before it collapses to form stars. A dust grain might drift through space for hundreds of millions of years before it's incorporated into a new star or planet. These are spans of time so long that human history, all of recorded civilization, is just the blink of an eye in comparison. It puts our own lives, our own worries, into a perspective that can be strangely comforting. We are part of this vast, slow process, made of the same dust, shaped by the same forces, but we don't have to carry the weight of it. We can simply be, for our brief moment, and that's enough. The clouds are also full of surprises. Astronomers have discovered complex organic molecules in dust clouds, molecules with dozens of atoms, including amino acids, the building blocks of proteins, and sugars, the building blocks of DNA. These molecules form in the clouds, on the surfaces of dust grains, or in the gas, through slow, patient chemistry. When a new star system forms and planets coalesce, these molecules are incorporated into the planets, delivered to their surfaces by comets and asteroids. It's possible, even likely, that some of the organic molecules necessary for life on Earth came from interstellar dust clouds, that we are not just made of stardust, but of the chemistry that happened in the cold, dark spaces between the stars. The dust clouds are also beautiful in ways that go beyond the visual. If you could translate the radio waves they emit into sound, you would hear a symphony of frequencies, each one corresponding to a different molecule, a different transition, a different piece of the cloud story. Astronomers do this, in a sense, by observing clouds at many different wavelengths, building up a picture not just of what the cloud looks like, but of what it's made of, how it's moving, how hot or cold it is, how dense, how active. It's a kind of cosmic listening, paying attention to the whispers of matter across the light years. Some clouds are isolated, drifting alone in the space between spiral arms of the galaxy, far from any major star-forming regions. These clouds are quieter, less disturbed, evolving slowly under their own gravity and the gentle pressure of the galactic environment. They might never collapse to form stars, or they might do so only after billions of years, when some chance encounter or disturbance finally tips the balance. They are patient, content to exist, to drift, to wait. Other clouds are part of giant complexes, vast networks of gas and dust that span huge regions of the galaxy. These complexes are the sites of the most vigorous star formation, where hundreds or thousands of stars are being born in a relatively small region of space. The clouds in these complexes are stirred and shaped by the feedback from the stars they create, a chaotic but ultimately self-regulating process that determines how many stars form and how quickly. The dust in these clouds is not just a scientific curiosity. It's also a practical concern for astronomers. Dust absorbs and scatters light, making distant objects harder to see. The center of our own galaxy, for example, is hidden behind thick clouds of dust, invisible to optical telescopes. But infrared light, with its longer wavelengths, can pass through dust more easily, and radio waves pass through almost unimpeded. So astronomers use these other wavelengths to peer through the dust, to see what lies beyond, to map the hidden structures of the galaxy. The dust is an obstacle, but also an opportunity, a challenge that has driven the development of new technologies and new ways of seeing. There's a certain poetry in the fact that dust, which we often think of as dirt, as something to be cleaned away, is in space the raw material of creation, the substance from which stars and planets, and ultimately life arise. It's a reminder that context matters, that value is not intrinsic but relational, that what seems insignificant in one setting can be profound in another. The dust under your bed is just dust, but the dust between the stars is the future, waiting to unfold. The clouds also have a role in the larger structure of the galaxy. They trace out the spiral arms, marking the regions where gas and dust are compressed by the galaxy's rotation, triggering waves of star formation. If you could see our galaxy from above, you would see the spiral arms lit up with young, bright stars, and threaded through with dark lanes of dust, the clouds from which those stars recently formed, and from which more stars will form in the future. The dust clouds are part of the galaxy's anatomy, as essential as the stars themselves. Some clouds are so dense and so cold that they emit almost no light at all, visible only by the way they block the light of stars behind them, or by the faint radio emission of molecules within them. These are called dark cores or Bach globules, small, compact clouds that are often on the verge of collapsing to form stars. They look like ink drops on the sky, small and round and utterly black. But inside them, the process of star formation is just beginning, slow and invisible, a secret unfolding in the dark. The dust grains themselves can be studied in the laboratory. Scientists have found microscopic grains in meteorites, grains that formed in other star systems and somehow made their way to our solar system, surviving the journey intact. These presolar grains, as they're called, can be identified by their unusual isotopic compositions, which don't match anything that formed in our solar system. By studying these grains, scientists can learn about the stars that made them, about the conditions in those stars' atmospheres, about the processes that created the elements. It's a way of holding a piece of another star in your hand, of touching the distant past. The clouds are also affected by cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light. When a cosmic ray hits a dust grain or a gas molecule in a cloud, it can ionize it, knocking off an electron and changing its chemistry. This ionization drives certain chemical reactions that wouldn't happen otherwise, adding another layer of complexity to the cloud's chemistry. The cosmic rays are like invisible rain, constantly falling on the clouds, stirring them, changing them, adding energy to the mix. There are clouds that are being torn apart by the gravity of passing stars or the tidal forces of the galaxy itself. These clouds are stretched and shredded, their material dispersed back into the general interstellar medium, where will eventually be gathered up by other clouds or by the gravity of the galaxy. Nothing in space is permanent. Even the clouds, vast and ancient as they are temporary structures, lasting for millions of years, but not forever, always forming, always dissolving, part of the endless cycle of matter and energy that is the galaxy. And there are clouds that are just being born, condensing out of the thinner gas of the interstellar medium, gathering together under their own gravity or compressed by some external force. These young clouds are less dense, less structured, still finding their shape, still settling into the patterns that will define them for the next few million years. They are the future, the next generation of star nurseries, waiting for their turn to create. The dust clouds remind us that space is not empty, that even the vast distances between stars are filled with matter, with potential, with ongoing processes that connect everything together. The atoms in your body were once part of a dust cloud, drifting through space, waiting to become part of something new. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it was forged in stars and then scattered into clouds and then gathered into the earth and then, eventually, into you. You are made of dust clouds in the most literal and beautiful sense. So as you lie here, breathing slowly, letting your thoughts settle, you can think of yourself as part of this vast, gentle cycle, this slow dance of matter through space and time. You are not separate from the cosmos. You are a piece of it, a brief, bright moment in its long story, made of the same stuff, shaped by the same laws, connected to everything that has ever been and everything that will ever be. And that connection, that deep kinship with the stars and the dust and the darkness between them, is something you can rest in, something solid and true and endlessly comforting. The clouds drift on, patient and slow, creating and dissolving, glowing and darkening, whispering their quiet secrets to anyone willing to listen. And we, for our part, can listen, can learn, can find in their vast stillness a kind of peace, a reminder that the universe is not hurried, not anxious, not worried about tomorrow. It simply is unfolding according to its own deep rhythms, and we are invited to be part of that unfolding for as long as we are here. The dust clouds hold within them a kind of memory, you see. Each grain that drifts through the darkness carries with it a record of where it has been, what stars have touched it, what cosmic events have shaped its surface. Scientists can read these tiny archives, examining the isotopes locked within the dust, understanding which supernovae contributed which elements, when certain stellar populations were active, how the galaxy has evolved over billions of years. It is like holding a library in your hand, except each book is smaller than a bacterium, and each page was written by a dying star. And the clouds themselves are not uniform, not at all. Within a single vast nebula, there are regions of different density, different temperature, different chemical makeup. Some areas are thick and opaque, blocking nearly all light, while others are thin and translucent, allowing starlight to filter through like sunlight through morning mist. These variations create structure within the cloud, lanes and filaments and pockets, each with its own character, its own story. The cloud becomes a landscape, a terrain of gas and dust, sculpted by gravity and starlight and magnetic fields into shapes both beautiful and strange. The magnetic fields that thread through these clouds are invisible, intangible, yet they play a profound role in shaping what happens within the dust. These fields are weak by everyday standards, far weaker than a refrigerator magnet. Yet across the vast scales of interstellar space, they exert influence. They guide the motion of charged particles. They resist the collapse of gas under gravity. They twist and bend the structure of the cloud itself. The dust grains, many of them carrying a slight electric charge, align themselves along these magnetic field lines, like tiny compass needles pointing along invisible threads that stretch across light years. This alignment of dust grains has a curious effect on starlight passing through the cloud. The light becomes polarized, meaning its waves vibrate in a particular direction rather than in all directions at once. Astronomers can measure this polarization, and from it, they can map the magnetic fields within the cloud, revealing the hidden architecture that supports and shapes the visible structure. It is a way of seeing the invisible, of understanding forces that leave no direct trace except in the subtle behavior of light, and matter. The clouds become not just objects to observe, but puzzles to decode, each observation revealing another layer of hidden complexity. Within the densest parts of these clouds, where the dust is thickest and the gas most concentrated, something remarkable happens with chemistry. The surfaces of dust grains become workshops for molecular construction. Atoms and simple molecules drift through the darkness, occasionally colliding with a grain, sticking to its icy surface. There, held in place, they can meet other atoms, react, form bonds that would be difficult or impossible in the emptiness of open space. The grain acts as a meeting place, a catalyst, a tiny laboratory where the building blocks of complexity are assembled. Water forms this way, hydrogen atoms meeting oxygen on the surface of a grain, bonding in H2O, freezing into ice that coats the dust. Ammonia forms, methane, carbon dioxide, and more complex molecules still, organic compounds, the carbon-based molecules that are the foundation of life as we know it, are constructed in these frigid workshops. Amino acids have been found in meteorites, and many scientists believe they first formed on dust grains in interstellar clouds, then were delivered to young planets when those planets swept up the material of their birth nebula. The clouds are not just star nurseries, but chemistry labs, places where the ingredients of life are patiently prepared. The timescales involved in this chemistry are long, slow, unhurried. A single molecule might take thousands of years to form, atom by atom, as the right ingredients happen to meet on a grain surface. But the clouds have time, immense stretches of time, and across millions of years, the chemistry proceeds, building up layers of ice and organic material on every grain. When eventually a star forms and planets coalesce, this material is incorporated into them, seeding the new worlds with water, with organic molecules, with a chemical foundation for life. We are, in a very real sense, made of processed stardust, assembled in the patient darkness of interstellar clouds. And the clouds are not isolated, not separate from the rest of the galaxy. They are part of a great cycle, a cosmic circulation that moves matter from stars to space and back again. Stars form from clouds, live their lives, then return material to space through stellar winds and supernovae. This material enriches the interstellar medium, adding heavier elements to the mix, then gradually cools and condenses into new clouds. These new clouds form new stars, which eventually return material again, and the cycle continues, generation after generation, each iteration slightly enriching the galaxy with heavier elements, with greater chemical complexity. Our own solar system formed from such a cloud, a nebula that had been enriched by previous generations of stars. The heavy elements in our bodies, the iron in our blood, the calcium in our bones, the carbon in every cell, were forged in stars that died before a sun was born, then spent millions of years drifting in interstellar clouds before being incorporated into the planets and eventually into living things. The clouds are the intermediaries in this grand cycle, the places where stellar death becomes stellar birth, where destruction becomes creation, where endings become beginnings. The clouds also play a role in regulating the overall activity of star formation in a galaxy. If star formation proceeded too quickly, a galaxy would exhaust its gas supply rapidly, forming all its stars in a brief burst, and then going quiet. But the clouds introduce delays, inefficiencies, pauses in the process. Much of the gas in a cloud does not form stars. It is dispersed by stellar winds, heated by radiation, stirred by magnetic fields, and remains in the interstellar medium. This inefficiency means that star formation proceeds slowly, steadily, over billions of years, allowing galaxies to remain active and vibrant across cosmic time. The dust within these clouds also affects the large-scale appearance of galaxies. When we look at a spiral galaxy edge-on, we often see a dark band running through its center. This is dust, concentrated in the galaxy's disk, absorbing the light of stars behind it. The dust dims the galaxy, makes it appear less bright than it would otherwise, and astronomers must account for this when measuring distances and luminosities. But the dust also makes the galaxy more interesting, adding texture and structure, revealing where the gas is concentrated, where new stars are forming, where the next generation of stellar systems will emerge. In our own Milky Way, dust clouds create the dark patches visible in the night sky, the apparent gaps in the river of stars. For thousands of years, people looked at these dark regions and thought they were simply empty, voids where no stars existed. It was only with the advent of modern astronomy that we understood these were not voids but clouds, vast accumulations of dust and gas that blocked the light of stars beyond. The darkness was not absence, but presence, not emptiness, but the raw material of creation, waiting patiently for gravity to gather it into new suns. The process by which a cloud collapses to form stars is governed by a delicate balance of forces. Gravity pulls inward, trying to compress the cloud. Pressure from the gas pushes outward, resisting compression. Magnetic fields resist collapse, as do turbulent motions within the cloud, chaotic flows, and eddies that stir the gas and prevent it from settling. For a cloud to collapse, gravity must overcome all these opposing forces, and this typically requires either a very massive cloud or some external trigger, a push from outside. Such triggers can come from various sources. A nearby supernova can send a shock wave through the interstellar medium, compressing clouds in its path, tipping the balance toward collapse. The spiral arms of a galaxy, where gas and dust pile up as they orbit, can compress clouds and trigger star formation. Even the collision of two clouds can provide the necessary compression. Once triggered, the collapse begins slowly, gently at first, then accelerating as the densest regions pull in more material, growing denser still, until finally the conditions for star formation are met. But not all clouds collapse. Many remain stable for millions of years, drifting through the galaxy, slowly evaporating as starlight heats their edges, slowly accreting new material from the surrounding medium. Some clouds are disrupted before they can form stars, torn apart by stellar winds or dispersed by passing shock waves. The clouds exist in a state of constant change, forming, evolving, dispersing, reforming, part of the dynamic, ever-shifting structure of the galaxy. The dust grains within the clouds are themselves constantly changing, growing and shrinking, gaining and losing material. In dense regions, grains collide gently, sticking together to form larger grains, a process called coagulation. These larger grains can grow over time, becoming pebbles, then boulders, eventually forming the seeds of planets. In regions exposed to intense radiation, grains can be eroded, their surfaces blasted away by energetic photons, their ice is evaporated, their size reduced. The grains are not static objects, but dynamic participants in the life of the cloud, constantly shaped by their environment. When a star finally does form within a cloud, it changes everything around it. The young star is often violent, energetic, surrounded by a swirling disk of gas and dust, shooting out jets of material from its poles at tremendous speeds. These jets plow into the surrounding cloud, creating shock waves, heating the gas, compressing it, sometimes triggering the formation of more stars nearby. The young star also emits intense ultraviolet radiation, which begins to ionize the gas around it, creating a glowing region called an H2 region, where hydrogen atoms are stripped of their electrons and the gas shines with a characteristic reddish glow. This radiation also begins to erode the cloud, pushing back against the material that gave the star birth. The process is called photoevaporation, and it gradually disperses the cloud, blowing away the gas and dust, revealing the young stars within. Over time, a stellar nursery transforms from a dark, opaque cloud into a bright cluster of young stars surrounded by glowing, tattered remnants of the nebula that formed them. The Orion Nebula is a beautiful example of this process in action, a cloud in the midst of being dispersed by the stars it has created, glowing brilliantly, visible even to the naked eye. The dust in these regions is heated by the young stars, and this warm dust glows in infrared light. This infrared glow is one of the primary ways astronomers study star formation, because infrared light can penetrate the dust that blocks visible light, allowing us to see into the hearts of stellar nurseries. Space telescopes equipped with infrared detectors have revealed the inner workings of these clouds, showing us protostars still gathering mass, disks of material around young stars where planets are forming, the intricate structures carved by stellar winds and jets. Around young stars, the dust in the surrounding disk begins to stick together, grain by grain, building up into larger and larger objects. This process of planet formation is slow and complex, but it begins with the simple dust grains that survive the star's formation. These grains collide gently in the disk, and if conditions are right, they stick, held together by weak forces, by icy coatings, by electrostatic attraction. Over time, these aggregates grow, becoming pebbles, then rocks, then planetesimals, objects kilometers across that have enough gravity to attract more material. Eventually, some of these planetesimals grow large enough to become planets. Rocky planets form in the inner regions of the disk, where it is too warm for ice to exist. Gas giants form farther out, where ice can survive, providing more material for building large cores that then attract massive atmospheres of hydrogen and helium. The dust, which began as tiny grains forged in dying stars, which drifted through interstellar clouds for millions of years, which survived the formation of a new star, finally finds its ultimate destination, incorporated into planets, into moons, into asteroids and comets, into the solid worlds that orbit the star. And on at least one of those worlds, around at least one star, the dust became part of something even more remarkable. It became part of living things, part of cells and organisms, part of creatures that could think and wonder and look up at the night sky and ask where they came from. The atoms in our bodies were once part of interstellar dust clouds, drifting in the darkness, patient and silent, waiting for the slow processes of cosmic evolution to bring them together, to organize them into the complexity of life. This connection is not poetic exaggeration, but literal truth. The carbon, nitrogen, oxygen, phosphorus, sulfur, iron, and trace elements that make up our bodies were formed in stars, dispersed into space, incorporated into interstellar clouds, processed on the surfaces of dust grains, then gathered into the solar nebula, then into the Earth, then into the first living cells, then passed down through billions of years of evolution to us. We are not separate from the cosmos, but part of it, made of it, shaped by the same processes that form stars and planets and galaxies. The interstellar dust clouds are still out there, still drifting, still forming stars, still preparing the ingredients for new worlds and perhaps new life. The galaxy is filled with them, hundreds of billions of solar masses of gas and dust spread across the spiral arms, concentrated in the disk, thinning out in the halo. Some clouds are being born now, condensing from the diffuse interstellar medium. Some are in the midst of forming stars, glowing and churning with activity. Some are being dispersed, their material returned to space to begin the cycle again. The clouds are patient. They operate on timescales so long that human history is but a flicker, a brief moment in their slow evolution. A cloud might drift for 10 million years before collapsing. It might take 1 million years to form a cluster of stars. might be dispersed over another million years. From our perspective, they seem almost eternal, unchanging, but they are constantly evolving, just very, very slowly. To understand them requires a shift in perspective, an ability to think in cosmic time, to see the galaxy not as a static photograph, but as a slow, majestic dance of matter and energy. And there is something deeply calming about this perspective. The clouds remind us that not everything must happen quickly, that patience is built into the fabric of the universe, that the grandest creations require time, vast stretches of time, and that this is not a flaw, but a feature. The clouds do not hurry. They cannot hurry. They simply exist, drifting, evolving, creating at their own pace, indifferent to any sense of urgency, and yet accomplishing transformations of staggering significance. When you look up at the night sky and see the Milky Way, you're seeing the combined light of billions of stars, but you are also seeing the dark patches between them, the dust clouds that thread through our galaxy. You're seeing the places where stars are being born, where planets are forming, where the building blocks of life are being assembled. You are seeing the past, because the light has taken years or centuries or millennia to reach you. And you're seeing the future, because in those dark clouds, the next generation of stars is beginning to form. The dust clouds connect us to the cosmos in the most fundamental way. They are the link between stars and planets, between the non-living and the living, between the past and the future. They are the places where the universe does its most important work, quietly, patiently, without fanfare, transforming the ashes of dead stars into the seeds of new worlds. And they do this not through violence or drama, but through the gentle, persistent action of gravity, chemistry, and time. There is a particular cloud that has captured the attention of astronomers for decades, a vast structure called the Taurus molecular cloud. It lies about 430 light-years from Earth, close by cosmic standards, and it is a relatively quiet stellar nursery, forming low-mass stars slowly and steadily. Unlike the violent, massive star formation regions like Orion, Taurus is gentle, peaceful, a place where stars are born without much fuss. It has been studied extensively because it allows astronomers to observe star formation in a calm environment, without the complicating factors of massive stars and intense radiation. The Taurus cloud is filamentary, composed of long, thin strands of gas and dust that stretch across dozens of light years. These filaments are where the densest gas is concentrated, and along them, like beads on a string, young stars and protostars are forming. The filaments themselves are thought to form through the action of turbulence and magnetic fields in the interstellar medium, creating a web-like structure that channels gas into dense lanes where gravity can take over and form stars. This filamentary structure appears to be common in molecular clouds, a natural consequence of the forces that shape them. Another famous cloud is the Coal-Sack Nebula, visible in the southern hemisphere, a dark patch in the Milky Way near the Southern Cross. It is one of the most prominent dark nebulae in the sky, easily visible to the naked eye as a dark void in the otherwise bright band of the Milky Way. The Coal-Sack is relatively close, about 600 light-years away, and it contains enough dust to completely block the light of stars behind it. Indigenous peoples of the Southern Hemisphere have long recognized the Coal-Sack and incorporated it into their mythology, seeing in it various shapes and stories, a reminder that humans have always noticed and wondered about these dark regions. The dust clouds are also important for understanding the overall structure and dynamics of the galaxy. By mapping where the clouds are, how they move, how dense they are, astronomers can trace the spiral arms of the Milky Way, understand how gas flows through the galaxy, predict where future star formation will occur. The clouds are tracers of the galaxy's large-scale structure, markers of the densest regions where matter accumulates and stars are born. They reveal the skeleton of the galaxy, the framework upon which everything else is built. In other galaxies, we can see dust clouds as well, dark lanes and patches that trace the spiral arms that mark the sites of star formation. In some galaxies, collisions with other galaxies have compressed the gas and dust, triggering intense bursts of star formation, creating brilliant, chaotic regions where thousands of stars are being born in a relatively small volume. These starburst galaxies are laboratories for studying star formation under extreme conditions, and the dust within them glows brightly in infrared light, heated by the intense radiation of countless young stars. Even in elliptical galaxies, which were once thought to be devoid of gas and dust, we now know that some amount of interstellar material exists. These galaxies have used up most of their gas-forming stars long ago, and they have little ongoing star formation, but they are not completely empty. Some gas and dust remains, often acquired from smaller galaxies that have been absorbed, and occasionally, in the very centers of these galaxies, small amounts of star formation still occur, a faint echo of the vigorous activity that characterized their youth. The dust clouds also play a role in the chemical evolution of the universe as a whole. In the very early universe, shortly after the Big Bang, only the lightest elements existed: hydrogen, helium, and traces of lithium. There were no heavy elements, no carbon, no oxygen, no iron, no silicon. The first stars formed from this pristine material, and when they died, they created the first heavy elements, dispersing them into space. These elements mixed with the remaining hydrogen and helium, forming the first dust grains, the first enriched clouds, the first second-generation stars. Over billions of years, generation after generation of stars has continued this process, each cycle adding more heavy elements, more chemical complexity. The interstellar medium has become progressively enriched, and the dust clouds that form from it have become more complex as well. The dust grains in a cloud today contain a rich mixture of elements, far more diverse than the grains that existed billions of years ago. This chemical evolution is essential for the formation of planets and life, because rocky planets and organic chemistry require heavy elements, and those elements are built up slowly over cosmic time through the life and death of stars and the patient accumulation of material in interstellar clouds. The clouds are also sensitive to the environment of the galaxy. In the inner regions, where the density of stars is higher, where supernovae are more frequent, where the radiation field is more intense, the conditions for cloud survival are harsher. Clouds can be disrupted more easily, heated more intensely, and the dust grains can be destroyed more rapidly. In the outer regions of the galaxy, where the environment is calmer, clouds can persist longer, remain colder, and the dust can survive in a more pristine state. This variation across the galaxy creates a diversity of environments for star formation, and the stars that form in different regions can have different properties as a result. There are also clouds in the space between galaxies, in the vast intergalactic medium. These clouds are much more diffuse than those within galaxies, but they exist, and they contain gas and some amount of dust. They are the remnants of material ejected from galaxies by supernovae and galactic winds, and they are also the reservoirs of gas that can be accreted by galaxies, fueling future star formation. The intergalactic medium is a vast, mostly empty frontier, but even there, the dust is present, a faint trace of stellar processes, a reminder that the influence of stars extends far beyond the galaxies themselves. The dust clouds continue their work in the quietest corners of the galaxy, and we can follow their influence through the way they shape light itself. When starlight passes through a dust cloud, it doesn't simply disappear or dim uniformly. Instead, the cloud acts as a cosmic filter, scattering blue light more efficiently than red light, allowing the longer wavelengths to pass through with greater ease. This is why stars seen through dust clouds often appear redder than they truly are, their light gently shifted toward the warm end of the spectrum. It's the same principle that gives us red sunsets here on Earth, but stretched across distances so vast that the light may travel for thousands of years through the dust before reaching our telescopes. The effect is called interstellar reddening, and it tells astronomers not only that dust is present, but how much of it lies between us and the distant stars. And within this reddening effect lies a deeper story about the sizes of dust grains themselves. The scattering of light depends intimately on the relationship between the wavelength of light and the size of the particle doing the scattering. Blue light, with its shorter wavelength, bounces off even the smallest grains, while red light, with its longer wavelength, can slip past those same tiny obstacles. By measuring how much a star's light has been reddened, astronomers can infer the typical size of the dust grains in the cloud, most of which are smaller than the wavelength of visible light itself. It's a gentle form of cosmic detective work, reading the fingerprints left by invisible particles on the light that has journeyed through them. The dust reveals itself not by what we see, but by what it quietly takes away. In some regions of space, the dust is so thick that it blocks visible light almost entirely, creating what appear to be dark patches or rifts in the Milky Way. These dark nebulae, as they're called, were once thought to be empty voids, regions where stars simply didn't exist, but we now know they are anything but empty. They are among the densest collections of dust and gas in the galaxy, so rich in material that they absorb nearly all the light from stars behind them. The Coalsack Nebula, visible from the southern hemisphere, is one such region, a dark smudge against the bright band of the Milky Way. To the unaided eye, it looks like a hole in the sky, a place where the stars have gone out. But in truth, it is a place where stars are waiting to be born, a nursery hidden behind a veil of dust so thick that only infrared light can penetrate it. When we turn infrared telescopes toward these dark nebulae, they come alive with hidden detail. The dust that blocks visible light glows warmly in the infrared, revealing intricate structures, filaments, and cores where gravity is slowly gathering material. Protostars, still wrapped in their dusty cocoons, shine brightly in these longer wavelengths, their heat radiating outward even though their visible light cannot escape. The dark nebulae, far from being empty, are among the most active and dynamic regions in the galaxy. They remind us that darkness in the cosmos is not absence. It is often presence, a thickness of matter so profound that it transforms the way we must look at the universe. The dust clouds also play a role in one of the most beautiful and mysterious phenomena in the night sky, the reflection nebulae. These are clouds of dust that lie near bright stars, close enough to be illuminated by their light, but not so close that the dust is destroyed by heat or radiation. The dust grains scatter the starlight in all directions, creating a soft, glowing halo around the star, often with a distinctive blue color. The blue tint comes from the same scattering effect that reddens distant starlight. Blue light, being more easily scattered, bounces off the dust grains and reaches our eyes, while the redder light tends to pass straight through. The result is a gentle, diffuse glow, like a street lamp shining through fog on a quiet night. One of the most famous reflection nebulae surrounds the Pleiades, a young cluster of stars visible to the naked eye. The stars themselves are bright and blue, and they illuminate a faint, wispy cloud of dust that was once thought to be the remnant of the cloud from which the stars formed. We now know that the Pleiades are simply passing through a dusty region of space, their light briefly illuminating the material they encounter on their journey through the galaxy. The Reflection Nebula is a chance meeting, a temporary partnership between stars and dust that will last only a few million years before the stars move on and the dust fades back into darkness. It's a reminder that even in the cosmos, some of the most beautiful sights are fleeting, the result of perfect timing and alignment. The dust clouds also influence the chemistry of space in ways that reach far beyond the clouds themselves. When cosmic rays, high-energy particles traveling at nearly the speed of light, strike dust grains, they can break apart molecules or ionize atoms, creating a cascade of chemical reactions. These reactions can produce new molecules, some of which are then released into the surrounding gas when the dust grain is heated or disturbed. In this way, dust clouds act as both shields and reactors, protecting some molecules from destruction while facilitating the creation of others. The balance between these processes helps determine which molecules are abundant in space and which are rare, shaping the chemical landscape of the galaxy over billions of years. Some of the molecules produced in and on dust clouds are surprisingly complex, including the building blocks of sugars and amino acids. These organic molecules, once thought to require the special conditions of a planetary surface to form, can actually be synthesized in the cold, dark environment of a dust cloud, given enough time and the right ingredients. The discovery of these complex molecules in space has shifted our understanding of how life's chemistry might have originated. Rather than starting from scratch on the early Earth, life may have had a head start, inheriting a rich inventory of organic molecules delivered by comets and meteorites, which themselves formed in dusty regions around the young sun. The dust clouds, in this sense, are not just the birthplaces of stars and planets, but also the kitchens where some of life's essential ingredients are first prepared. And the dust continues to teach us about the history of the universe itself. By studying the composition of dust in distant galaxies, astronomers can trace the evolution of heavy elements over cosmic time. In the early universe, shortly after the Big Bang, there was no dust at all. The only elements present were hydrogen, helium, and trace amounts of lithium. Dust requires heavier elements like carbon, oxygen, silicon, and iron, and those elements are forged only in the cores of stars. As the first generations of stars lived and died, they released these heavy elements into space, where they condensed into the first dust grains. Over billions of years, as more stars formed and died, the amount of dust in the universe gradually increased. By measuring the dust content of galaxies at different distances, and therefore different points in cosmic history, astronomers can watch this enrichment process unfold, seeing how the universe slowly became more chemically complex. In some of the most distant galaxies, observed as they were when the universe was only a billion years old, astronomers have found surprisingly large amounts of dust. This was unexpected, because there hadn't been much time for many generations of stars to form and die. The presence of this early dust suggests that the first stars, which were much more massive and short-lived than stars today, produced and dispersed heavy elements very quickly. These massive stars may have exploded as supernovae after only a few million years, flooding the early universe with dust and setting the stage for the formation of the next generation of stars. The dust, even in the earliest epochs of cosmic history, was already playing its role as a recycler and enabler, ensuring that the universe would not remain simple and pristine, but would grow ever more intricate and alive with possibility. Closer to home, the dust clouds in our own galaxy have a rhythm and structure shaped by the Milky Way's spiral arms. These arms are not solid structures, but rather regions of higher density where gas and dust are compressed as they orbit the galactic center. When a dust cloud enters a spiral arm, it is squeezed by the increased pressure, and this compression can trigger the collapse of dense cores within the cloud, leading to star formation. The spiral arms are like cosmic assembly lines, places where the raw material of the galaxy is processed and transformed into stars. Once the stars form, they heat and illuminate the surrounding dust, creating the bright nebulae that trace out the spiral structure. Over time, the stars drift out of the spiral arm, but the dust remains, waiting for the next wave of compression to begin the cycle again. This process gives the galaxy a kind of breathing rhythm, a slow, steady pulse of star formation that has continued for billions of years. The dust clouds are an essential part of this rhythm, responding to the gravitational forces that shape the galaxy and enabling the transformation of gas into stars. Without dust, the galaxy would look very different. Star formation would be less efficient, and the interstellar medium would be hotter and more ionized, less able to cool and collapse. The dust, by facilitating cooling and shielding molecules from radiation, keeps the galaxy's star formation engine running smoothly, ensuring that new stars continue to be born even as old stars fade away. And there is something deeply calming about the scale of these processes. The dust clouds do not hurry. They do not rush to form stars or collapse into planets. They drift through the galaxy at their own pace, shaped by gravity and starlight, magnetic fields and cosmic rays, slowly cycling matter from one form to another. A single dust grain might spend millions of years floating through space before it becomes part of a star, and then, after the star dies, it might be released back into space to begin the journey again. This patience, this willingness to take the long view, is built into the very fabric of the cosmos. The universe is not in a hurry, and neither are the dust clouds that fill it. We can also find comfort in the fact that the dust clouds are, in a very real sense, universal. Every galaxy we observe contains dust, from the smallest dwarf galaxies to the largest ellipticals. Even in the space between galaxies, in a vast intergalactic medium, there are traces of dust blown out by galactic winds or stripped away by gravitational interactions. Dust is not a rare or exotic phenomenon. It is a fundamental component of the universe, as common as stars and gas, and just as essential to the cosmic story. Wherever there are stars, there will eventually be dust, and wherever there is dust, there is the potential for new stars, new planets, and perhaps new life. The dust clouds also have a role in one of the most profound questions we can ask, which is whether we are alone in the universe. The same processes that form dust clouds and trigger star formation also create the conditions for planets. And many of those planets will be rocky worlds like Earth, with the potential to support liquid water and life. The organic molecules found in dust clouds, delivered to young planets by comets and asteroids, provide a chemical foundation that life can build upon. In this way, the dust clouds are intimately connected to the question of life's origins, not just on Earth, but potentially on countless other worlds throughout the galaxy. Every time a dust cloud collapses to form a new star, it is also sowing the seeds for possible life, creating the raw material and the conditions that might, given time, lead to biology. And this connection makes the dust clouds feel less remote, less abstract. They're not just distant objects to be studied through telescopes. They are part of our own history, the ancient ancestors of the solar system and the Earth. The dust that filled the cloud from which the sun formed eventually became the ground beneath our feet, the air we breathe, the water we drink, and the bodies we inhabit. When we look up at the night sky and see the faint glow of a nebula or the dark silhouette of a dust cloud, we are looking at a process that made us possible. We are, in a very literal sense, children of the dust, shaped by the same forces that shape the stars. The dust clouds also remind us of the interconnectedness of the cosmos. Nothing in the universe exists in isolation. Stars are born from dust, and dust is born from stars. Planets form from the debris of stellar birth, and life, if it arises, is built from the chemistry of dust and gas. The atoms in our bodies were forged in the cores of ancient stars, released into space when those stars died, gathered into dust clouds, and eventually incorporated into the solar system. We are made of star stuff, as the saying goes, but we are also made of dust, the quiet, patient material that links one generation of stars to the next, one planet to another, one form of matter to the next. The dust clouds are the threads that weave the cosmic tapestry, connecting past and future, star and planet, matter and life. There's also a certain poetry in the way dust clouds interact with time. Because light takes time to travel, when we observe a distant dust cloud, we are seeing it not as it is now, but as it was when the light left it. A cloud 1,000 light years away appears to us as it was 1,000 years ago. In this way, the dust clouds are like cosmic time capsules, preserving a record of the galaxy's history. By observing clouds at different distances, we can watch the evolution of the galaxy unfold, seeing how dust and gas have changed over time, how star formation has waxed and waned, how the chemical composition of the universe has grown richer and more complex. The dust clouds are not just objects in space. They are moments in time, frozen in the light that reaches us across the vast distances of the galaxy. And yet, despite all this grandeur and scale, the dust clouds remain fundamentally gentle. They do not explode or collide with violence. They do not burn or radiate intense energy. They simply exist, drifting through space, slowly changing, slowly building, slowly giving rise to new structures and new possibilities. There is no drama in a dust cloud, no sudden events or catastrophic transformations. Everything happens gradually, on timescales so long that they dwarf human history. This slowness, this patience, is part of what makes them so relaxing to contemplate. They remind us that not everything in the universe is fast or loud or urgent. Some of the most important processes are quiet and slow, unfolding over eons, invisible to the hurried eye, but profound in their effects. The dust clouds also have a kind of resilience. They can be disrupted by shock waves from supernovae, heated by nearby stars, or torn apart by galactic collisions, but they always reform. The material that makes them up is recycled endlessly, scattered and gathered, dispersed and condensed, in a cycle that has no clear beginning or end. Even when a dust cloud collapses to form stars, not all of the material is used. Some of it is blown away by stellar winds, some is left behind in the form of planets and asteroids, and some is simply returned to the interstellar medium, ready to become part of the next cloud, the next generation of stars. The dust is patient, and it is persistent, always ready to begin again. In the coldest, densest parts of dust clouds, where temperatures drop to just a few degrees above absolute zero, the dust grains can become coated with layers of ice. These icy mantles are made of frozen water, carbon monoxide, carbon dioxide, methane, and ammonia, simple molecules that condense out of the gas and stick to the grain surface. The ice provides a smooth, stable surface where more complex chemistry can occur. Atoms and molecules that land on the ice can slide around, meet each other, and react, forming new compounds that would be difficult or impossible to create in the gas phase. Some of these reactions are driven by the energy of cosmic rays or ultraviolet light, which can break bonds and rearrange atoms, creating a slow but steady drizzle of new molecules into the surrounding cloud. One of the most important molecules formed on icy dust grains is molecular hydrogen, the most abundant molecule in the universe. In the gas phase, it is very difficult for two hydrogen atoms to meet and stick together long enough to form a molecule. They need a third body to carry away the excess energy, and in the thin gas of space, such three-body encounters are rare. But on the surface of a dust grain, the grain itself can absorb the energy, allowing the two hydrogen atoms to bond. The grain acts as a matchmaker, bringing atoms together and stabilizing the resulting molecule. Once formed, the molecular hydrogen can be released back into the gas, where it plays a crucial role in cooling the cloud and allowing it to collapse. Without dust grains to catalyze this reaction, the universe would have far less molecular hydrogen, and star formation would be much less efficient. The icy mantles on dust grains can also be processed by ultraviolet light, which breaks apart the simple molecules and allows the fragments to recombine into more complex forms. This process, called photochemistry, can produce organic molecules like formaldehyde, methanol, and even simple sugars. When a dust cloud eventually collapses to form a star and planets, these organic-rich grains are incorporated into comets and asteroids, which can then deliver their cargo to young planets. On Earth, this delivery of organic molecules may have played a role in the origin of life, providing the raw materials that early biochemistry needed to get started. The dust clouds, in this way, are not just passive collections of matter. They are active participants in the chemistry of life, quietly assembling the building blocks that will later be used by living organisms. The dust grains can also be destroyed, broken apart by high-energy photons or collisions with fast-moving atoms. When a grain is shattered, it releases the atoms and molecules locked within it, enriching the surrounding gas. This process, called sputtering, is most common near hot stars or in regions where shock waves are passing through. The destruction of dust grains is balanced by their creation in the winds of dying stars, maintaining a rough equilibrium in the interstellar medium. The grains are constantly being created and destroyed, a cycle of birth and death that mirrors the cycle of stars themselves. Nothing in the cosmos is permanent, not even the dust, but the cycle ensures that the essential ingredients are always available, always ready to be used again. And there is something soothing about this cycle, this endless recycling of matter. It means that nothing is ever truly lost. The atoms that make up a dust grain today might have been part of a star a billion years ago, and they might become part of a planet a billion years from now. The universe is thrifty, using and reusing the same material over and over, transforming it from one form to another, but never discarding it. The dust clouds are part of this great recycling system, gathering up the debris of old stars and preparing it for the birth of new ones. They are the universe's way of keeping things tidy, ensuring that the raw materials of creation are always in circulation. The magnetic fields that thread through dust clouds also have a calming, organizing influence. These fields, though incredibly weak by everyday standards, are strong enough to guide the motion of charged particles and to align dust grains. Because many dust grains are slightly elongated, they can be torted by the magnetic field, lining up like tiny compass needles. This alignment affects the way the grains scatter light, producing a phenomenon called polarization. By measuring the polarization of starlight that has passed through a dust cloud, astronomers can map the direction and strength of the magnetic field within the cloud. These maps reveal a hidden architecture, a network of field lines that crisscross the cloud, shaping its structure and influencing how it collapses. The magnetic fields also provide support against gravity, slowing down the collapse of a dust cloud and giving it time to fragment into smaller pieces. Without magnetic fields, clouds might collapse too quickly, forming a single massive star instead of a cluster of smaller ones. The fields act as a kind of brake, adding an extra layer of complexity to the star formation process and ensuring that a wide range of stellar masses are produced. This diversity is important because different types of stars play different roles in the galaxy. Massive stars produce heavy elements and explode as supernovae, while smaller stars like the Sun live for billions of years, providing stable environments where planets can evolve and life can emerge. The magnetic fields and dust clouds, by influencing how stars form, help shape the character of the galaxy itself. In some dust clouds, the magnetic fields are so well organized that they create long, narrow filaments, structures that look like threads or fibers stretching across the cloud. These filaments are often the sites of active star formation, with dense cores strung along them like beads on a string. The filaments seem to channel gas and dust toward the densest regions, feeding the growing protostars and helping them accumulate mass. The origin of these filaments is still a topic of research, but they appear to be a natural consequence of the way turbulence and magnetic fields interact in a cloud. The turbulence creates shock waves that compress the gas, and the magnetic fields guide the flow, creating elongated structures that are both beautiful and functional. The dust clouds also have a role in shaping the large-scale structure of the galaxy. The distribution of dust is not uniform. It is concentrated in the spiral arms and in the galactic plane, where most of the star formation occurs. This concentration of dust affects how we see the galaxy, obscuring our view of the galactic center and making it difficult to observe distant parts of the Milky Way in visible light. But the dust also traces the structure of the galaxy, highlighting the regions where gas and stars are most abundant. By mapping the dust, astronomers can map the galaxy's architecture, seeing how matter is distributed and how it flows from one region to another. The dust also plays a role in the energy balance of the galaxy. It absorbs starlight and re-emits it as infrared radiation, effectively redistributing energy from hot, bright regions to cooler, darker ones. This process helps to regulate the temperature of the interstellar medium, preventing it from becoming too hot or too cold. The dust acts as a kind of thermostat, keeping conditions stable and conducive to star formation. Without dust, the galaxy would be a very different place, hotter and more ionized, with less molecular gas and fewer sites of active star formation. The dust, by mediating the flow of energy, helps maintain the balance that allows the galaxy to continue evolving and producing new stars. And as we think about all these roles that dust clouds play, from shielding molecules to catalyzing reactions, from forming stars to feeding planets, we begin to see them not as mere collections of particles, but as integral, active components of the cosmic ecosystem. They are the connective tissue of the galaxy, linking stars and gas, past and future, matter and energy. They are patient, resilient, and endlessly creative, quietly doing the work that makes the universe a place where complexity and beauty can emerge. There is something deeply reassuring about this, the idea that the universe is not chaotic or random, but organized by processes that, while slow and subtle, are reliable and persistent. The dust clouds also invite us to slow down, to adopt their pace, to think in terms of millions of years rather than minutes or days. In our daily lives, we are often rushed, pressured to move quickly, to make decisions, to act. But the dust clouds remind us that some things cannot be hurried, that some processes require patience and time. A star takes millions of years to form, a planet billions of years to become habitable, and life, once it begins, evolves over eons. The dust clouds, by operating on these vast timescales, teach us the value of patience, the importance of allowing things to unfold at their own pace. They are a lesson in slowness, in the quiet accumulation of small changes that, over time, lead to profound transformations. The dust clouds drift through seasons of their own, measured not in months, but in millions of years. When a massive star explodes nearby, the shock wave pushes through the cloud like a gentle hand reshaping sand. The dust compresses, then slowly expands again, carrying the memory of that distant violence in its altered density. These compressions can trigger new rounds of star formation, turning destruction into creation across timescales so vast they feel like patience itself. The cloud responds to each cosmic event with the slowness of deep geological time, never hurrying, always adapting. Within the densest regions of some clouds, the dust grains grow thick coatings of ice and frozen molecules. Layer upon layer accumulates over millions of years, each grain becoming a tiny archive of chemical history. Water ice, carbon monoxide ice, methanol ice, ammonia ice, all freeze onto the grained surfaces in the profound cold. These icy mantles can grow thicker than the original grain itself, transforming a speck of silicate or carbon into a miniature comet. When stars eventually form and warm these regions, the ice is sublimate, releasing their stored molecules into the newborn planetary systems. It is a slow preparation, a patient gathering of ingredients for future worlds. The dust clouds interact with cosmic rays, those high-energy particles streaming through the galaxy from distant supernovae and other violent events. When a cosmic ray strikes a dust grain, it can break chemical bonds on the surface, creating reactive sites where new chemistry becomes possible. The grain becomes slightly altered, its surface more active, more ready to facilitate molecular construction. This happens grain by grain, impact by impact across billions upon billions of particles. The cumulative effect is subtle but profound. The entire cloud becomes a vast chemical laboratory, activated by the gentle bombardment of particles traveling at nearly the speed of light. Some dust grains contain presolar grains, particles that formed around other stars before our sun even existed. These ancient travelers survived the destruction of their parent stars, the journey through interstellar space, the collapse into our solar nebula, and the formation of meteorites that eventually fell to Earth. Scientists can identify them by their unusual isotopic ratios, signatures that mark them as older than our solar system. Holding a meteorite that contains presolar grains means touching matter that drifted through interstellar clouds before our world existed. The dust clouds preserve these ancient particles, carrying them forward through cosmic time like precious seeds. The clouds experience what might be called weather, though on scales and timescales utterly unlike Earth's atmosphere. Density variations ripple through them like slow waves. Temperature fluctuations spread across light years over millions of years. Magnetic field lines twist and reconnect in processes that take longer than human civilizations endure. This cosmic weather shapes the cloud structure, creating the filaments and clumps that eventually become stellar nurseries. It is weather without wind as we know it, without seasons we could recognize. Yet it follows physical laws as reliable as those governing Earth's climate, just expressed across vastly different scales. The dust grains themselves can be magnetic, particularly those containing iron or other metallic elements. These magnetic grains align themselves with the cloud's magnetic field, all pointing in roughly the same direction, like tiny compass needles. This alignment affects how the cloud absorbs and emits polarized light, allowing astronomers to map the magnetic field structure of distant clouds without ever visiting them. The grains respond to forces we cannot see, organizing themselves according to invisible lines of magnetic influence that thread through the galaxy. It is a quiet ordering, a gentle alignment that happens grain by grain across light years. Within the coldest, densest cloud cores, the dust grains become so crucial to chemistry that they essentially run the show. Gas phase reactions slow to near in the extreme cold, but surface reactions on dust grains continue, facilitated by the grain's ability to absorb excess energy. Atoms land on grain surfaces, slide slowly across the icy coating, meet other atoms, bond, and form molecules that then drift back into the gas. The grains act as matchmakers and catalysts, bringing together atoms that would rarely meet otherwise. In this way, the solid particles enable the gas phase chemistry that fills the cloud with complex molecules. The dust does not merely exist within the cloud. It actively shapes the cloud's chemical evolution. Some clouds contain regions where the dust-to-gas ratio differs from the galactic average. Perhaps a previous generation of stars enriched the region with extra dust, or perhaps gas has been blown away by stellar winds, leaving the dust behind. These variations affect how the cloud will evolve, how quickly it will cool, how efficiently it will form stars. The ratio matters because dust and gas work together. The dust cools the gas shields the dust, and together they create the conditions for gravitational collapse. A cloud with more dust cools more efficiently and might form stars more readily. The balance between solid and gas determines the cloud's destiny. The clouds participate in what astronomers call the galactic fountain, a cycle where gas and dust rise above the galactic disk, cool, and fall back down. Supernova explosions and stellar winds push material upward into the galactic halo, where it cools and eventually rains back down onto the disk, often forming new clouds in the process. This fountain operates on timescales of tens to hundreds of millions of years, slowly mixing the galaxy's material, redistributing elements, and creating opportunities for new generations of star formation. The dust clouds are not permanent fixtures, but temporary gatherings of material in this vast, slow cycle. Within some clouds, astronomers have detected dust grains with crystalline structures, minerals that formed at high temperatures and somehow ended up in the cold interstellar environment. These crystals likely formed in the hot outflows of dying stars, then were ejected into space where they cooled and joined the interstellar medium. Their presence in cold clouds tells a story of journeys across temperature extremes, from stellar furnaces to the coldest regions of space. The grains carry their crystalline order into the darkness, tiny fragments of structure in the diffuse cloud, proof that even in the cold and dark, the universe preserves echoes of heat and light. The dust clouds interact with the galaxy's spiral arms in a slow, graceful dance. As the galaxy rotates, clouds move through spiral density waves, regions where matter temporarily compresses. When a cloud enters a spiral arm, it experiences increased pressure from surrounding gas, which can trigger compression and star formation. The cloud may spend tens of millions of years crossing through the spiral arm, slowly responding to the changing environment, forming stars in response to the gentle squeeze. Then it emerges on the other side, perhaps diminished, perhaps dispersed by the stars it created, continuing its orbit around the galactic center. Some of the organic molecules found in dust clouds are chiral, meaning they come in left-handed and right-handed versions, mirror images of each other. Interestingly, some clouds show slight excesses of one-handedness over the other, a puzzle that connects to the fact that life on Earth uses predominantly left-handed amino acids and right-handed sugars. The origin of this asymmetry might trace back to processes in interstellar clouds, perhaps involving circularly polarized light from nearby stars interacting with molecules on dust grain surfaces. If so, the handedness of life itself might have been determined in the quiet darkness of a dust cloud billions of years ago. The clouds can contain what astronomers call Bok globules, small, dense, dark clouds silhouetted against brighter backgrounds. These globules are typically only a light year or so across, tiny by interstellar standards, and contain enough material to form one or a few stars. They appear as dark spots against the Milky Way, small pockets of concentrated darkness. Many Bok globules are actively forming stars within their dark interiors, hidden from optical view, but detectable in infrared light. They are like seeds within the larger cloud, concentrated nodes where the process of star formation has advanced further than in the surrounding regions. The dust grains experience forces we rarely consider. Radiation pressure from starlight pushes on them, a gentle but persistent force. Gravity pulls them toward concentrations of mass. Magnetic fields guide their alignment. Gas pressure buffets them. Electrostatic forces attract and repel them from other grains. Each grain responds to this complex field of forces, drifting through space along trajectories determined by the sum of all influences. The result is a slow, complex dance, billions upon billions of particles moving in response to the physical laws that govern the universe, creating patterns and structures across light years. In regions where new stars have formed, the dust clouds begin to change character. The ultraviolet light from young, hot stars heats the nearby dust, causing it to glow in infrared light. The radiation pressure pushes dust grains away, creating cavities and bubbles in the cloud. Stellar winds blow channels through the gas and dust. Slowly, over millions of years, the stars clear away their birth material, dispersing the cloud that created them. Eventually, the cloud may be entirely disrupted, its material scattered back into the interstellar medium, ready to join new clouds in the future. The cycle continues, creation and destruction in slow alternation. Some clouds show evidence of turbulence, chaotic motions that cascade from large scales to small. Supersonic flows create shock waves that compress and heat the gas and dust. Vortices form and dissipate over thousands of years. This turbulence provides support against gravitational collapse, helping to hold the cloud up even as gravity tries to pull it together. The balance between turbulence and gravity determines when and where stars will form. The turbulence itself may be driven by stellar winds, supernova shock waves, or the gravitational energy of the collapsing cloud. It is chaos in slow motion, disorder that somehow leads to the ordered process of star formation. The dust clouds contain information about the galaxy's history, encoded in the composition and structure of the grains. The ratio of different elements reflects the history of stellar nucleosynthesis in the galaxy. The presence of certain molecules indicates past events, nearby supernovae, passages through spiral arms, encounters with other clouds. By studying dust clouds throughout the galaxy, astronomers can reconstruct the chemical evolution of the Milky Way, tracking how the abundance of heavy elements has increased over billions of years as successive generations of stars have lived, died, and enriched the interstellar medium. Within the densest cloud cores, conditions approach those of the early universe in one specific way: the simplicity and purity of the chemistry. With temperatures near absolute zero and densities still far lower than any laboratory vacuum, these regions represent some of the most extreme environments in the current universe. Yet in this extremity, simple molecules form with remarkable efficiency. Hydrogen molecules, carbon monoxide, water, the basic building blocks assemble in the cold and dark. It is a reminder that complexity does not require warmth or density, that the universe can build intricate structures even in the most seemingly hostile environments. The clouds experience time differently than we do, if we can speak of experience at all. A process that takes 1,000,000 years is, to the cloud, perhaps like a moment to us. The slow collapse of a cloud core, the gradual drift of grains, the patient accumulation of ice mantles. These are the cloud's natural rhythms. From this perspective, the sudden flash of a star's birth is a quick event, and the star's entire main sequence lifetime is merely a brief period of brightness before the long darkness returns. The cloud's time is geological, cosmic, measured in the slow turning of the galaxy and the gradual evolution of stellar populations. Some dust grains are fluffy aggregates, loosely bound collections of smaller grains that stick together when they collide gently. These aggregates can be 10 or 100 times larger than individual grains, yet they remain fragile, held together by weak van der Waals forces. Their fluffy structure gives them a large surface area relative to their mass, making them especially effective at absorbing and scattering light. In the stillness of the cloud, these aggregates can grow slowly over time, gently collecting more grains, building larger and larger structures. This is the first step toward planet formation, the gentle aggregation of dust into larger bodies. The clouds are not uniform in their isotopic composition. Different regions may have slightly different ratios of isotopes. Carbon, 12 versus carbon, 13, oxygen, 16 versus oxygen, 18, and so on. These variations reflect the cloud's history, the contributions of different stellar sources, and the chemical processes that have occurred. By mapping isotopic ratios across a cloud, astronomers can trace the mixing of material from different sources, identifying regions that have been enriched by nearby supernovae or that retain more primitive compositions. The cloud becomes a map of its own history, written in the subtle language of isotopes. In some clouds, the dust grains develop mantles rich in organic material, complex carbon-based molecules that form through reactions on the grain surfaces. These organic mantles can include molecules similar to those found in living cells, amino acid precursors, sugar-related compounds, components of nucleotides. The grains become tiny factories of prebiotic chemistry, assembling the molecular building blocks of life in the cold darkness. When these grains are eventually incorporated into forming planets, they deliver this organic material to the new worlds. The clouds are not just star nurseries, but also the birthplaces of the chemistry that will later enable life. The dust clouds respond to the galaxy's magnetic field on the largest scales, but they also generate their own local magnetic field structures through the motion of ionized gas. As the cloud contracts, it drags magnetic field lines inward, concentrating and amplifying the field. This process, called magnetic flux freezing, means that collapsing clouds develop stronger magnetic fields in their densest regions. The magnetic field can then influence the further collapse, channeling material along field lines, creating the disk structures around forming stars, and launching jets perpendicular to the disk. The cloud's magnetic field is both shaped by the collapse and a shaper of the collapse, a feedback loop that determines the final architecture of the stellar system. Some clouds are so large and massive that they contain enough material to form thousands or even millions of stars. These giant molecular cloud complexes are the largest gravitationally bound structures in the galaxy, spanning hundreds of light years and containing hundreds of thousands of solar masses of material. Within these complexes, star formation occurs in many locations simultaneously, creating clusters and associations of young stars. The Orion Molecular Cloud Complex, visible to the naked eye as the Orion Nebula, is one such region, a vast stellar nursery where stars are being born across a region larger than many constellations. Yet even these giants are temporary, lasting perhaps only tens of millions of years before their stars disperse them. The dust grains can act as tiny laboratories for studying surface chemistry under conditions impossible to replicate on Earth. The combination of extreme cold, high vacuum, and exposure to ultraviolet light and cosmic rays creates a unique chemical environment. Scientists use laboratory experiments to simulate these conditions, freezing molecules onto cold surfaces and irradiating them, then comparing the results to observations of interstellar clouds. This work reveals that grain surface chemistry is rich and complex, capable of producing molecules that would never form in the gas phase alone. The grains are not passive containers, but active participants in cosmic chemistry. Within the clouds, there are regions where the balance tips toward destruction rather than creation. Ultraviolet light from nearby stars can break apart molecules faster than they form. Cosmic rays can ionize atoms, disrupting chemical bonds. In these regions, the chemistry becomes simpler, dominated by atoms and simple molecules. Yet even destruction serves a purpose in the cosmic cycle. It returns complex molecules to simpler forms, resets the chemistry, and makes the atoms available for new combinations. The clouds contain regions of both synthesis and breakdown, creation and destruction, all operating simultaneously in different locations. The dust clouds are part of the galaxy's cooling system. When gas and dust mix in the interstellar medium, the dust radiates away energy in the infrared, cooling the gas. This cooling is essential for the gas to collapse and form new clouds and stars. Without dust, The interstellar medium would be hotter and more diffuse, and star formation would be much less efficient. The dust grains, by radiating away energy, help the galaxy maintain a cycle of star formation. They are tiny cooling elements, each one removing a minute amount of heat, but collectively they shape the thermal structure of the entire galaxy. Some clouds show signs of being shaped by the magnetic field on large scales, forming elongated structures aligned with the field direction. These magnetic filaments can stretch for tens of light years, channeling gas and dust along the field lines. Star formation in these filaments often occurs in a chain-like pattern, with stellar nurseries spaced along the filament like beads on a string. The magnetic field provides a scaffold, a structure that guides where and how the cloud will collapse. It is an invisible architecture, detectable only through its effects on the visible matter. The clouds contain dust grains at every stage of their life cycle. Some are freshly formed, recently ejected from a dying star, their surfaces still pristine and crystalline. Others are ancient, their surfaces pitted and altered by billions of years of exposure to cosmic rays and ultraviolet light. Some are growing, accumulating ice mantles and organic coatings. Others are being destroyed, shattered by shock waves, or evaporated by stellar radiation. The cloud is a mixture of all these stages, a population of grains with different histories and different futures, all drifting together through the darkness. In the quietest regions of the clouds, far from any stars, the dust and gas reach an equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang. The temperature settles at just a few degrees above absolute zero, as cold as anything in the universe can be without active cooling. In this profound cold, motion slows, reactions nearly cease, and the cloud enters a state of deep cosmic stillness. It is a silence beyond any silence on Earth, a cold beyond any winter, a darkness beyond any night. Yet even here, molecules slowly form, atoms occasionally meet, and the patient chemistry of the cosmos continues. The dust clouds are resilient. They can be compressed by shock waves, heated by nearby stars, irradiated by cosmic rays, and yet they persist. The grains can be destroyed, but new grains form. The molecules can be broken apart, but they reform. The cloud can be dispersed, but the material joins new clouds elsewhere. This resilience is built into the nature of the interstellar medium. There is so much space, so much material, so much time, that no single event can permanently erase the clouds. They are part of the galaxy's fundamental structure, as persistent as the stars themselves, though far more diffuse. Some clouds contain regions where the dust has been partially destroyed, leaving behind only the most refractory grains, those made of materials that can withstand high temperatures and harsh radiation. These regions reveal the toughest survivors, grains of graphite, silicon carbide, or corundum that endure conditions that vaporize their more fragile neighbors. By studying these survivors, astronomers learn about the most extreme environments within clouds, the boundaries where stellar radiation is so intense that it fundamentally alters the dust population. These are the frontiers between the cloud and the stars, zones of transition where the cloud's material is being processed and transformed. The dust clouds participate in the galaxy's chemical memory. Elements created in one generation of stars are incorporated into clouds, then into the next generation of stars and planets. This process has been repeating for billions of years, gradually enriching the galaxy with heavy elements. The first dust clouds in the early universe contained almost no elements heavier than hydrogen and helium. Today's clouds are rich in carbon, oxygen, silicon, iron, and dozens of other elements, all created in stars. The clouds carry this chemical memory forward, ensuring that each new generation of stars has access to a richer palette of elements than the last. Within the clouds, there are gradients of every property, density, temperature, composition, magnetic field strength, velocity. These gradients drive flows and create structure. Gas flows from low-pressure regions to high-pressure regions. Heat flows from warm areas to cold areas. Material drifts along magnetic field lines. These flows are slow, often imperceptible even on astronomical timescales, but they shape the cloud's evolution. The gradients ensure that the cloud is never truly static, always evolving, always redistributing its material and energy in response to internal and external forces. The dust grains can preserve molecules for immense periods. A molecule frozen onto a grain surface in the cold depths of a cloud can remain there for millions of years, protected from destructive radiation and isolated from reactive partners. When the grain eventually becomes part of a forming planetary system, the molecule may be delivered intact to a planet or comet. This means that molecules formed in one interstellar cloud can survive to reach the surface of a planet in a completely different stellar system. The grains are time capsules, preserving chemical information across cosmic distances and durations. Some clouds are illuminated by the combined light of all the stars in the galaxy, a faint but pervasive glow called the galactic background light. This light is too faint to significantly heat the dust, but it is enough to maintain a minimum temperature and to drive some low-level chemistry. Even clouds far from any individual star are not in complete darkness. They are bathed in this gentle, diffuse light, a reminder that they are part of a galaxy containing hundreds of billions of stars. The background light connects every cloud to the larger galactic community, ensuring that no region is entirely isolated. The clouds contain dust grains that will one day become part of living organisms. The carbon in these grains may become part of DNA molecules. The oxygen may become part of water in a cell. The iron may become part of hemoglobin in blood. The connection between interstellar dust and life is not metaphorical, but literal. The atoms are the same, pass from stars to clouds to planets to living things. The dust clouds are not separate from life, but part of its deep history, the source of the raw materials that make biology possible. In regions where star formation has recently occurred, the dust is being transformed by the energy output of the young stars. Ultraviolet light alters the grain surfaces, breaking chemical bonds and creating new reactive sites. Infrared light heats the grains, causing them to radiate more intensely. Stellar winds physically push the grains away, creating expanding shells and bubbles. Over time, these processes clear away the dust in the immediate vicinity of the stars, creating transparent regions where the stars become visible. The dust retreats, pushed back by the energy of the stars it helped create, a cycle of creation and dispersal. The clouds are threaded with filaments, long, narrow structures where the density is higher than the surrounding regions. These filaments appear to be ubiquitous in molecular clouds, a fundamental aspect of cloud structure. Star formation occurs preferentially in these filaments, particularly where filaments intersect or where the filament density exceeds a critical threshold. The filaments may form through the interaction of turbulence and gravity, or through the influence of magnetic fields, or through a combination of processes. They are the skeleton of the cloud, the framework along which the cloud's material is organized. Some dust grains contain water ice that formed billions of years ago and has remained frozen ever since. This ice has never been liquid, never flowed, never evaporated. It went directly from gas to solid in the cold of the cloud, and it will remain solid until some future event, incorporation into a comet, delivery to a planet, heating by a nearby star, changes its state. This ice is older than our solar system, older than the sun, a frozen memory of ancient clouds that drifted through the galaxy long before Earth existed. The dust clouds are part of the galaxy's ecosystem, if we can use that term for a system of matter and energy rather than living things. They interact with stars, gas, magnetic fields, and radiation in complex feedback loops. Stars form from clouds, then disperse clouds, then enrich clouds with new elements, then trigger new cloud formation through their deaths. The clouds respond to these influences, evolving, adapting, changing over time. It is a system of cycling matter and energy, operating on vast scales, maintaining a kind of balance even as individual components come and go. Within the clouds, there are moments of transition, thresholds where one state changes to another. A cloud core becomes dense enough to collapse. A grain becomes large enough to feel gravity differently. A molecule becomes complex enough to exhibit new properties. These transitions are not sudden but gradual, occurring over thousands or millions of years. Yet they represent fundamental changes in the nature of the system. The clouds exist in a space of possibility, always near some threshold, always potentially on the verge of transformation. The dust grains scatter light in ways that depend on their size, shape, and composition. Small grains scatter blue light more than red, which is why clouds can appear blue when illuminated by nearby stars. Larger grains scatter all colors more equally. Elongated grains produce polarized light. By measuring how light is scattered, astronomers can infer the properties of the grains without ever collecting a sample. The grains reveal themselves through their interaction with light, their properties encoded in the photons that reach our telescopes. Some clouds are being compressed by the weight of the gas above them in the galactic disk. This gravitational pressure, combined with the cloud's own self-gravity, can trigger collapse and star formation. The process is slow, taking millions of years, but it is steady and inevitable. The cloud gradually becomes denser, its center contracting, its structure evolving toward the formation of stars. This is gravity operating on the largest scales, the same force that holds us to Earth, here shaping the destiny of clouds light years across. The clouds contain regions where the chemistry has produced molecules so complex that they approach the threshold of what we might call prebiotic. Long carbon chains, ring structures, molecules with dozens of atoms, all formed through the patient accumulation of reactions over millions of years. These molecules are not alive, not even close, but they are steps along the path from simple atoms to the complex chemistry that life requires. The clouds are laboratories of chemical evolution, exploring the space of possible molecules, creating the raw materials for future complexity. In the densest cloud cores, the dust grains may begin to stick together when they collide, the first step toward planet formation. The collisions are gentle, the velocities low, and the grains can adhere through weak forces. Over time, these aggregates grow from microscopic grains to millimeter-sized particles to centimeter-sized pebbles. This is the beginning of a process that will eventually produce planets, but it starts here in the quiet darkness of the cloud, with the gentle collisions of dust grains. The planets of future solar systems are being assembled grain by grain, in slow motion, in the cold. The dust clouds are places of potential. They contain the material for stars, planets, and life. They harbor complex chemistry and intricate structure. They respond to forces on every scale, from quantum interactions on grain surfaces to galactic magnetic fields. They are ancient yet constantly renewed, diffuse yet capable of concentration, cold yet full of latent energy. They are patient, operating on timescales that dwarf human history, yet they're dynamic, constantly evolving. They are the galaxy's raw material, its chemical laboratory, its nursery for new worlds. And in their vast, slow existence, there is something deeply calming. The clouds do not hurry. They do not struggle. They simply drift, respond, evolve according to the laws of physics that govern all matter. They are part of a process larger than themselves, a cosmic cycle of matter and energy that has been operating for billions of years and will continue for billions more. They remind us that the universe is patient, that great things happen slowly, that there is time enough for stars to form, for planets to coalesce, for life to emerge and evolve. As you rest, you might imagine yourself drifting through such a cloud, surrounded by the gentle darkness, the faint glow of distant stars filtered through dust, the profound silence of space. There is no urgency here, no deadline, no rush. There is only the slow drift of particles, the patient accumulation of ice on grained surfaces, the gradual contraction of cloud cores that will, in time, become stars. It is a place of deep peace, where time moves differently, where the universe takes its time, where everything happens at the pace it needs to happen. The dust clouds ask nothing of us. They do not require our attention or understanding. They existed long before we did, and will exist long after we are gone. Yet in studying them, in learning their nature, we connect ourselves to the larger universe. We recognize that we are made of the same elements, shaped by the same forces, part of the same cosmic story. The clouds are not separate from us, but part of our deep history, the source of the matter that makes up our bodies, our world, our sun. And so, as you settle into rest, you can take comfort in the knowledge that the dust clouds continue their slow work. Stars are forming, molecules are assembling, grains are drifting through the darkness. The universe is patient, and there is time enough for everything. You are safe. You are part of this vast, slow process, and you can rest knowing that the cosmos continues its gentle, steady evolution. The clouds drift on, and so can you, into the peaceful darkness of sleep.